He is a professor and holds a Joe J. King Chair in the Engineering University in Texas in Austin. He has over 35 years of experience in practice and research in geotechnical and geosynthetics engineering. His research focuses on transportation geotechnics, geosynthetics, unsaturated soils, expensive clays, and environmental engineering. He served as the president of the International Geosynthetic Society, and he has authored more than 500 scientific papers and several book chapters. He has been awarded 3 patents and has received numerous prestigious awards, and one of them is the Presidential Early Career Award for Scientists and Engineers from the President of the United States. And the IGS recently established the Zornberg Lecture, an honorary lecture recognizing his contributions to the discipline of geosynthetics. Now I would like to invite you, Jorge, to speak, and you will tell us about the sustainability benefits of geosynthetics in roadway applications.
Thank you very much. I'm going to be waiting now for... Can you hear me well? Yes? Yes. Great. So, there you go. First, thank you for having me and having us here. It is such a pleasure to be here in the Netherlands, and particularly we're going to be talking about a very, very special series of topics. I'm going to be talking about sustainability. I'm going to be talking about geosynthetics, and I'm going to be talking about roadways. I'm going to try to pull them all together and see how they can, we can work with all of them. Let me start with roadways. It turns out that roadways is a massive asset. Actually, I understand that when it comes to public assets, roadways is the most significant public asset that we have, at least in the US for sure, and I suspect in the world. So here is the ranking of the network length, and the total length of all roads is 64 million kilometers. To have a sense of what this means, out of this, look at that. If you look at the first line here, US has approximately 10% of the world roads. Now, how big is this? Let's take the circumference of the Earth in its largest diameter at the equator. It is 40,000 kilometers. What does this mean? It means that if we were to get the 64 million kilometers around the equator, once, twice, 3 times, 10 times, we would need to go 1,600 times around the equator in order to understand or start thinking of how big of an asset this is. These are roads that need to be constructed. These are roads that need to be maintained. The typical design life of a roadway is 15 years. So they are designed to be reconstructed. Let's talk about geosynthetics. Second aspect of my presentation. I'm going to be there are many different wonderful types of geosynthetics, but I'm going to be talking about those that are used for roadway applications. That includes geotextiles, and that includes geogrids. Now, where do these geotextiles and geogrids get into the roadway? Well, what is a roadway? A roadway is a multi-layer system. And essentially, statics tells us that any load that goes on top of the asphaltic layer will make it to the subgrade. That's the law of physics. That's statics. That's easy. The issue is that really what matters is the contact pressure of that load here at the top of the subgrade. So the job of this structural package is to extend the load in an area as wide as possible in order so that the contact pressures are as low as possible. All right, but where can geosynthetics help us in building better roads? We define geosynthetics, or an important aspect of geosynthetics are their functions. And this is because the functions, once we identify the function of a geosynthetic, we are almost there. Not there, but almost there in identifying the right properties. It's a long way to identify what are the right functions of the geosynthetic for a given application. And roadways are particularly confusing because there are so many different applications that it may get confusing to identify what are the right functions to work. But we can use them as separators if the objective is to keep dissimilar materials separate. We can use it as reinforcement if we want them to develop tensile loads, and essentially we want to avoid collapse or reaching high strains. They can help with stiffening. They are also going to develop tensile loads, but now the objective is low strains, and the main objective is to control deformations, control displacements. These are more mechanical benefits, functions that geosynthetics can provide. But geosynthetics can also help in the hydraulic side. They can provide filtration, essentially working to minimize problems associated with cross-plane flow and carrying particles with that cross-plane flow. They can work as barriers, and essentially just preventing the passage of water. And finally, they can provide as in-plane drains. And a roadway designer knows that the presence of water is a very significant problem. So anything that we can do to eliminate the moisture from our structural package, we're going to get a better road from the mechanical point of view. All right, so, and the third topic that I'm going to speak about, but I'm going to go very quickly on this, is about carbon emissions. So we are talking about equivalent carbon content. And this is not the only way, but one of probably the most common way of quantifying the gas emissions that affect global warming, for example. And this is the historical perspective from the 1700s until 2022. This is the latest one as published by the Global Carbon Budget last year. So if we look at what happened, blue is the US, orange and brown are the two subsets of Europe, the European Union and Europe excluding the European Union. Until the 1900s, they were the only responsibles for the emission of carbon gases. That is also true around the 1950s. Still, significant increase in the quantity of CO2 emissions, but still the US and Europe contributing the most. We get into the 1980s, and it is only 40 years ago, is that other players starting getting into the carbon emissions. And in 1922, last year, we can see that the US and Europe are kind of a third of the contributor of the carbon emissions worldwide, with the big players now being in Asia, including particularly China and India. So, I'm not going to get more into this. I just want to tell you why it is going to be important for me to tell you how to compare the carbon emissions, the carbon audit of roadway solutions that involve and those that do not involve geosynthetics. So this is a different way of looking at that, at the same data, but in this case shown as a percentage. As we can see, in the 1700s, mainly Europe, blue is the US, and here we get in 2022 as a fraction. This is as a percentage of the contributions for the CO2 emissions. Very good. So what I'm going to do right now, I'm going to identify 6 different applications involving geosynthetics in roadways. These are not simple applications. It's not, oh, give me a geosynthetic, I'll improve the performance of the roadway. No, what aspect of the roadway you want to improve. Only at that point that I will know what are the functions that I need, and only after I know the functions is that I will know what are the properties. I'm going to focus on the following, on 6 of them. Mitigation of reflective cracking in structural asphalt overlays. How many of you do know what is roadway design? Any idea, vague concept of roadway design? Okay, just to understand how much I need to, okay. All right, so we're going to start by looking at the mitigation of reflective cracking on structural asphalt overlays. Then, second, stabilization of unbound aggregate layers. Third, and I'm going from the top down in the structural package, so an asphaltic layer, unbound aggregates. Then I get to the interface between the unbound aggregates and the subgrade. Reduction of layer intermixing, reduction of moisture in structural layers, very different applications. Then if I have soft subgrades, stabilization of soft subgrades, and then mitigation of distress due to shrink swell subgrades. From the place that I am, the main issue is expansive clays. In here, but this is the same problem as frost heave. So it is problems associated when the subgrade changes volume. I'm going to walk you through one example of each one of these 6 very different applications of how geosynthetics work in roadways. And for these different alternatives, these are real projects. These are real projects in which designers came up with 2 alternatives, one with and the other without geosynthetics. These 2 alternatives, according to the designers, were deemed to be equivalent from the performance point of view. So they ended up choosing the geosynthetics, but because it was the most cost-effective. I'm going to go back to that evaluation of alternatives, but I'm also going to evaluate 1/3 element in the design. Not only performance, not only cost. The third element is how do they fare against each other in terms of sustainability. And let's see what happens. That's the drill of what I'm going to be doing today. So essentially, I'm going to do carbon audits. I'm going to show you the results of carbon audits of pairs of alternatives in 6 different applications. Now, I'm going to go very quickly, but it's not just me. This is still in press, but it is already available online. The information that I'm going to be showing you here is available in this very recent paper. All right, so first application, mitigation of reflective cracking in asphalt overlays. What are we going to be doing? If you know what is an asphalt overlay, essentially we're going to mill, once before the roadway reaches its ultimate design life, what we can do is to mill the surface of the roadway and apply a fresh overlay of asphalt. That will extend the design life of the roadway. But there is a problem. There is a problem that this fresh asphalt is placed on top of pre-existing cracks. This creates a stress concentration that may cause a propagation, a reflection of the pre-existing cracks into the recently brand new asphalt overlay. And we do not want that. And geosynthetics have been traditionally used to prevent or minimize or retard this problem associated with reflective cracking. So let me show you very, very briefly, and I'm going to go extremely briefly in the mechanism for each application, because I want to convey that we're not doing magic. We are not just doing what we did because we saw that it worked. We're doing it because we know how the mechanisms work to make it work. So this is what is going to happen. If we do not have a geosynthetic and we have a pre-existing crack, and here we place a new asphalt overlay, very quickly, because when the wheel comes and here is a crack, when the wheel comes in here and I'm going to shear right before this crack, and when I'm on top of the crack, I'm going to bend that crack. And when I'm passing beyond the crack, I'm going to shear, but in the other, reversing the direction. So this is very demanding for the brand new asphalt overlay, and consequently, we're going to propagate that crack. What the geosynthetic will do is essentially will develop tension so that rather than having that stress concentration, triggering of a crack is an energy concept. So rather than having that stress concentration at a very localized point, we're going to extend. We're going to extend the area over which that straining occurs, and we're going to avoid the triggering of a crack. That's one of the mechanisms. That's not the only one, but I'm going to focus on this one. So essentially, now that we understand the mechanism, is that we can only at this point that we can talk about functions. The function in this case is going to be reinforcement, because reinforcement, we are going to be dealing with comparatively high strains. There is a different mechanism that I didn't mention here that is called stress relief, just for you to know that there is more than one mechanism, and there is a third mechanism that is called barrier. But I'm going to focus on this reinforcement, the tension development as the one mechanism. So I'm going to take you now to Texas, near the place that I live. This is actually in the Austin district of the Texas Department of Transportation. And I'm going to talk to you about one important road. It's actually this road it was particularly important because this serves the energy sector, fracking. And what the energy sector requires is suddenly comparatively small roads or low volume roads suddenly need a significant increase in capacity. And the best way, rather than reconstructing the road, is to add structural capacity on top of the existing one. This takes us to asphalt reinforcement. So SH21 is about an 18 miles. This is around 30 kilometers? Yeah, 30 kilometers. And it's going from the border of this county to the end of this county across SH21. This is Lee County. And an important, and I'm not going to talk about this, but an important aspect in this project that in addition to having been designed to have asphalt reinforcement also, we took the opportunity to do some highly instrumented test sections. So you will if you're interested in this topic, you will hear a lot about SH21 in a few years. So what is the challenge with this particular application? It's one specific application. We need to retard or minimize or hopefully eliminate the reflection of the cracks. But there's one more thing. Since we're having this reinforcement to avoid the reflective cracking, does it provide any additional structural capacity? Everyone knows that the answer is yes, but we do not know how to quantify it. It is only now that we're starting to quantify the improvement of this reinforced asphalt to the increase in the structural capacity. We're going to try to do that. So in this particular project, the design requirement was to minimize the reflective cracking and hopefully increase the structural capacity. The conventional design was essentially adding a reasonably thick, 127 millimeters. This is 5 inches of asphalt. That's more than what is needed for the transportation from the capacity point of view, but it's essentially to minimize the reflective cracking. What is the alternative? If you add a geogrid reinforcement, essentially you are trimming 50 millimeters or so of that new asphaltic layer. So how are we going to compare? Just so you know very quickly how this is constructed. So here you need to do some milling. Then you're going to apply a tack coat. Then you are going to install, in this case, it was a polymeric geogrid, the one that was installed. And finally, you're going to construct the asphalt overlay, essentially the same approach, using the same equipment that you would construct it without the geosynthetic. So let's do the carbon audit. 2 design alternatives that the designers considered, and they ended up going for the geosynthetic solution for cost evaluation. So they deemed that the cost of a geogrid layer was more effective from the cost financial point of view than 2 inches, 50 millimeters of asphalt. But let's see what happens if we compare the carbon content of these two solutions. Again, here we have the conventional design and the geosynthetic design. These are the different components. So if we do, I'm not going to walk you through how we did this carbon audit, but essentially here you have in blue the material, the source, the carbon embodied carbon in the materials themselves. Then we have the transportation in orange, and then we have the construction. Materials carry, and we're only talking about the materials for the overlay, not for the entire structural package, carry the significant burden. Any time that we see asphaltic layer, think of embodied carbon. The asphalt carries a lot of embodied carbon. So any inch, any centimeter of asphaltic layer that we can drop, we're significantly saving in embodied carbon. But let me show you what this means as well. So essentially, in the conventional design, the entire, because it's just asphalt, an asphaltic layer, the entire source comes from the asphaltic layer. If we go to the geosynthetic solution, we decrease the contribution provided by the asphaltic layer. We have a contribution from the geogrid, but we save this green 32%. 32% of the embodied carbon of the entire project was saved by having chosen. And again, the designers didn't think of embodied carbon when selecting a solution. They just did it based on performance and cost. But by doing so you save 32% of the embodied carbon in the solution. What does it mean? The way that it was quantified is the embodied carbon of a lane kilometer is 22 tons of CO2 equivalent. Just for you to know, 1 ton of CO2 is essentially half an hectare of forest. It's essentially the carbon that is sequestered by half of an hectare of forest in a year. All right, so we have application number 1. Let me walk you through a second application of geosynthetics in roadways, which is the stabilization of unbound aggregate layers. The objective. What do we ask for this unbound aggregate layer? We ask, give me stiffness. I want stiffness. Why? Because stiffness will distribute the load in a wider area. So the objective of the use of geosynthetics for this particular application is to provide an initial increase, and equally or more important, to minimize or avoid the decrease of the modulus of the unbound aggregate layer, the base and the subbase. So how does this work? And it's not trivial how this works. There were many competing mechanisms that the academic and industry areas were debating what is the right mechanism. We know that it works. We didn't know why. We need to know why it works, because without that, we cannot choose the right functions. But this is how it works. There is consensus on this. The consensus is on a mechanism that is called lateral restraint. This is how it goes. So you have a non-stabilized road base, and with the cyclic loading that takes place, we are going to have a tendency for the aggregates. These are clean aggregates. The only reason that they are stiff is because they are confined. But over time, there will be some tendency for the aggregates to displace laterally. And this is a domino effect. So if we have that lateral displacement, we have a loss in confinement. If we have a loss in confinement, we have a loss in modulus. If we have a loss in modulus, we have a highly concentrated load, and that leads to the early failure of my roadway. Instead, what the geosynthetic will do is essentially will prevent or minimize these lateral movement. That's why we call this mechanism lateral restraint. So only now that we know the mechanism is that we can go to the function. And the function is only one. And the function will be stiffening. We want to add stiffness, or the capability of gaining stiffness, to our unbound aggregate layer. All right, let me take you to an example, a project. This is in Ohio, also in the US, for stabilization of unbound aggregate. This is near Lake Erie, and it's a 4 kilometers road and 2 lanes. And the big challenge in this particular project is that because it is very close to Lake Erie, and I do not know because I live in Texas, but as I understand it, there is a phenomenon that is the lake effect snow. So the construction season in this area is very, very limited. It's very limited. It's only a few months where the construction can take place. So the construction was estimated to take place over 3 years, 3 summers. Only the construction would take place during the summer. So the requirements were to remove the old pavement and a thick subgrade layer and to replace it with high quality material. That was the job. So the conventional design would be that. No geosynthetic, an excavation of 900 millimeters, and then a replacement with these 2 different types, 2 different qualities of aggregate, and finally, an asphaltic layer. This was the alternative solution that was considered, using geosynthetics. Essentially, what they did is they shaved off 150 millimeters of aggregate, of each one, actually half of the thickness of these 2 different types of aggregates, because a geogrid was adopted, keeping, and probably this is a mistake from the point of view of embodied carbon, keeping the thickness of the asphaltic layer. An alternative could have been, let's reduce the thickness of the asphaltic layer rather than reducing the thickness of the base. But we didn't know any better, or the designers didn't know any better. They were just focusing on cost and performance. All right, so very quickly, the construction involves a geosynthetic stabilized base. This was the placement of the aggregate on top of the geosynthetic material. The construction time was reduced from 3 summers construction season to 2 summers. One third less. Not only was more inexpensive, it was also faster. Let's do the carbon audits and see what happens. So here we have the conventional design and the design using geosynthetics. And this is how they fare. This is the difference. The significant content still is dominated by the embodied carbon of the asphaltic layer that didn't change in the two solutions. So essentially, for the conventional solution, this black portion, this is the contribution to the embodied carbon by the asphaltic layer. And this is the contribution by the aggregate layers. And there was some additional small contribution. This small contribution is because this was an excavation, so that carries also some embodied carbon. So we are not going to touch this. So the entire effort will be to decrease the embodied carbon only on the aggregate layers. And this is the solution that after using the geosynthetic solution. A savings of 11% on the project embodied carbon. But don't think that this is small. This is actually more when we look at the tons per tons of embodied carbon, is more than the previous project, 30 tons of embodied carbon per lane kilometer. Very, very significant reduction. Third application, so I walked you through minimizing, application number 1, minimizing the asphaltic layer, minimizing the reflective cracking, the asphalt overlay. And then then I talked to you about stabilization of unbound aggregate layers, now avoiding intermixing. We want to avoid the contamination of the base material. here is the mechanism that will take place. Because without a geosynthetic separator, fines will be pumped into the base, and aggregate particles will sink into potentially a soft subgrade material. Here it is. Okay. So instead, this is a very, very simple solution. All we're going to be asking for this geosynthetic is just be a separator. So with a geosynthetic separator, essentially we may avoid that intermixing. So now that we know this, essentially what we're asking is separation and filtration. And these are essentially the geosynthetics that fulfill this requirement, even though they need to have some characteristics. Essentially what we are asking to function as a separator is the geosynthetic should just exist. If the geosynthetic exists, it will work as a separator. Let me take you to another project. This is kind of a more difficult project to quantify because typically we're not going to replace any layer as we did in the previous one. In the previous ones, we replaced a fraction of the asphaltic layer. In the second, we replaced a fraction of the unbound aggregate. This is different. This is going to work with performance. So we will need some additional data. Let me take you to this site in Virginia. And the challenge was how to quantify the benefit of a geotextile separator. We know that it works. We do not know why. And this is what these researchers did. So essentially, we're going to have that the conventional design to achieve essentially the expected design life of not exceeding a 20 millimeters rotting depth. That is a design life based on serviceability. In order to achieve that, in the conventional design, they needed not only to have the initial asphaltic layer, but replacing twice that asphaltic layer with an asphalt overlay. What the geotextile achieved is essentially keeping for the same initial asphaltic layer, essentially not having to go back and do the asphalt overlay. So this was the only way to quantify this is by getting data, which is very difficult to obtain. So here what we have is rotting depth versus number of cycles. And here we have the control section without geosynthetics and the section with a geotextile. And if our design criterion is not to exceed 20 millimeters of rotting depth, what this is telling us is essentially the number of cycles of a standard axle was 55,000, while with a geotextile it was 100,000, over 100,000, which was the required one, the required number of easels for the design life of this structure. So let's compare the alternative. The only difference between these two alternatives is not at the end of construction they are the same. Only one has a geotextile. Actually, at the end of construction, the embodied carbon of the geosynthetic one is slightly higher because one has a geotextile, the other doesn't. The difference is going to come when we account for the maintenance. And the difference is very significant. And the difference is going to be in materials. The embodied carbon has a significant, it contributes, asphalt contributes significantly to the carbon audit. So here is asphalt, and this is base, and this is subgrade. When we go for the geosynthetic solution, essentially we have eliminated going back over the design life twice and having to replace a fraction of the surface in the asphaltic layer. 44 tons of embodied carbon per lane kilometer. Everything is normalized for 1 lane, 1 kilometer. Significant contribution. Another application, this is 4th out of 6. Improving drainage, providing in-plane drainage. This is not easy. This is not easy because we're not draining, like maybe in the Netherlands you have that problem. Maybe your road will be below the water table. In most of the world, that's not the case. In most of the world, really the water table is somewhat deep, but still you have problem with water. And what you want is to decrease the moisture content, a high moisture content of a subgrade. And that's not trivial, because a typical drain would not do the job. So here's the idea, is that if we have a presence of moisture, for example, coming through capillarity, coming to the structural package, that the presence of moisture decreases the modulus, and the decrease in modulus increases the deflection and the rutting. The idea is that if you can eliminate that moisture before it makes it to the structural package, then you're doing a good job. So essentially, now that we know this, we go to the functions. You will have some separation, filtration, and the most important, in-plane drainage. But this is not an easy way to do in-plane drainage, because we need to really, we're not draining free water. We're stealing moisture. We're stealing moisture from an unsaturated soil. And we can only fight suction. The soil the water is held in the soil by suction. The only way to steal that moisture from the soil is with suction. The geotextile does not provide, a conventional geotextile does not provide suction. But some newcomers to the geosynthetic market can provide suction. This is how it works. If we have a geotextile, typically we're going to have yarns and pores in between those yarns. That's what we quantify with, we call it transmissivity. That's not what we're talking about. Let's go to a yarn. A yarn is a bunch of fibers. The water could go in those yarns. That's not what we're talking about. We're going to talk about, let's go to one fiber. Let's go to one fiber. But the cross-section of that fiber is special. It's so special that it has grooves. Think of these grooves as having higher surface tension, capillary tubes, having the capability of working as a capillary tube. It's not this volume of water, that's when it's free water. We're going to be talking about this volume of water. Very small fluxes, very small. My friends in the US, they do not know what is a liter. So what essentially I tell them is that, how much water? Well, for every 30 centimeters, 1 foot, don't expect any more than 5 bottles of water per day. So that is as little water as we're getting. Let me take you very quickly through a case history, because I know that I'm running out of time. Reconstruction of this site, at this site with a high water table. In this particular case, this is the conventional design that required a special drainage aggregate, and by having this special enhanced lateral drainage geosynthetic, the thickness of that aggregate was decreased. This is the concept. A weakening geotextile will weak the moisture that is not above the water table, is moisture under suction. Insulation, and here is the evidence of the moisture being released. Okay, so let's compare, and I'm going to go very quickly. So this is the comparison. This is a comparison in the carbon audit, very significant. They have eliminated essentially a significant fraction of the aggregate. This is the conventional solution. It includes the drainable base. The drainable base was a particularly expensive and hard to obtain aggregate, and this is the conventional aggregate. And essentially, the geosynthetic solution got rid of this expensive, hard to get aggregate, and instead added, here we have only a thicker, but in here we have the solution, the savings. Subgrade, do you have the computer here? I'm going to skip some slides. So I'm going to skip 2 important applications. I'm going to skip 2 important applications because I'm running out of time. One is going to be stabilization of the soft subgrade. Trust me, the answer is that the geosynthetics fare better than the conventional solution. The second is one that is particularly relevant for me, is how to mitigate problems associated with expensive clays. And trust me, geosynthetics the solution with geosynthetics does better. So I'm going to take you now to a summary. At the end, this is what I have to show you. I would have walking you through a solution involving the mitigation of reflective cracking and the stabilization of unbound aggregates and the reduction of layer intermixing and the reduction of moisture and the stabilization of soft subgrades and the mitigation of distress due to expansive soils. In all of them, the geosynthetic solution had a lower embodied carbon than the conventional solution. So this is what I'm going to invite you. Let's do a few calculations. Let's do a few calculations, and I'm going to do some very, very important assumptions. Consider the following. Let's consider, but this is a big assumption, that the 6 cases that I've shown you are representative of the applications, of these types of applications. In that case, I'm going to take this average reduction of all the 6 applications. This was the average embodied carbon that was reduced, 26 tons of embodied carbon. Another assumption. That's the embodied section per embodied, that's embodied carbon per project. I don't want per project, I want per year. I'm going to take a typical design life of a road that is 15 years, so I'm going to divide that contribution of reduction on embodied carbon into 15 years. So that takes me an average, and again, assuming that the cases that I showed you are representative, takes me to an average annual reduction of 1.75 tons of embodied carbon per lane kilometer per year. And one more assumption. Let's assume that every road in the world now realizes that because of cost, because of performance, and because of embodied carbon, they need to incorporate geosynthetics in their solutions. So this takes us to an annual average reduction of 225 million tons of embodied carbon per year. What does that mean? Well, let me tell you what that means. This is the same of the carbon that is sequestered by 100 million hectares of forest. What does that mean? Well, let's take the area of the Netherlands. This is equivalent to 24 times the area of the Netherlands per year if all the roads in the world were to use geosynthetics, and in my opinion, they should. So, in conclusion, in road applications, geosynthetics have been shown to improve, often very significantly, the performance. In roadway applications, geosynthetics have generally, not always, but generally, led to cost-effective solutions. Finally, geosynthetics have consistently led to more sustainable solutions. A different way of saying this third item is the following. Not only geosynthetics in roadways can reduce the embodied carbon, but the volume of roadways in the world is so significant that the potential benefits to global warming of using geosynthetics in roadways is truly massive. And with that, I thank you for your attention.